new bottoms, control, something like that. So do you see my recording bottom?
Yes.
Yes.
Okay. Yeah. Okay, it's great. So 1 second. So dear all, I would like to welcome you to our webinar number 8 in 2025 in regards to automated feature selection and curve prediction with experienced eye in interactive petrophysics software. This webinar will be presented by Mr. Andy McDonald from Geoactive company. My name is Mazen Hilali. I'm a senior petrophysicist with the local international in WINSCONET 2 project in Basra, Iraq. I will leave the floor to Dr. Mohammed Jawad Zain Abidin, our VP of Technology with SPWLA Iraq. The floor is yours, Dr. Mohammed.
Thank you, Mr. Mazen. Hello, everybody, our distinguished guests. It's my privilege to welcome you to today's session organized by the SPWLA Iraq. My name is Mohammed Jawad Zainul Abidin, and I serve as the Vice President of Technology for the SPWLA Iraq. I hold a PhD in petroleum engineering, and I'm a senior faculty member in the Department of Petroleum Engineering at the College of Engineering, University of Kirkuk. Today is Monday, the 24th of November, 2025, and we are pleased to convene the 8th edition in our 2025 webinar series. Today's presentation, titled Automated Feature Selection and Curve Prediction with Experienced Eye in IP, will be delivered by Mr. Andy McDonald at Geoactive Limited. Welcome again, Mr. Andy McDonald. Dear attendees, we would like to draw your attention to the following important points. Kindly keep your camera and microphone turned off throughout the webinar. Please note that the session will be recorded. If you have any questions, you are welcome to type them in the chat box. The lecturer will address them during the question and answer segment at the conclusion of the webinar. Additionally, please be informed that a link will be to join the SPWLA Iraq community on LinkedIn will be shared in the chat box during the presentation. Thank you, Mr. Mazen. The floor is yours.
Thank you, Dr. Mohammed. Much appreciated. I will just make like a very quick presentation. Okay. I will just share the screen. Let's see. Can you see my screen, Dr. Mohammed?
Now, yes, but I think some our guests they wrote that no sound at all. Maybe there is a technical problem.
I can't hear you.
Okay, that's good.
Miss.
Everything is here.
Sound okay. Thank
no
you.
problem.
Picture.
Okay.
That's
great.
Good.
That's great. You can hear me, Dr. Mohammed?
Yes. Mr.
Yeah, you
Mazen.
can see this. Yeah, you can see the presentation slide, this one?
Yes. Sure.
Okay, so I would like to welcome our attendees and Mr. Andy again. And I would like to thank Geoactive to accept our invitation to present their capabilities about AI/ML features in the IP software. This webinar, as mentioned, will be automated feature selections and care prediction with experienced eye and IP presented by Mr. Andy McDonald. He's a senior petrophysicist with Geoactive, and for sure he can present himself more than we can do. This is our, not 7 actually, it is our eighth webinar. For this year, and the focus was all on machine learning and AI application in petrophysics domain. We're still communicating to get one more or 2 extra webinar before the year end, but we didn't get any confirmation till now. Okay, if we didn't get confirmation, this will be the last one for this year. and I hope you a Happy New Year in a very advance. If not, we'll see you again next month. As usual, there will be a special learner certificate for any attendees have attended of our 6 or more of our webinar, and will be sent email about this one. And we are welcoming anybody like to join Iraq chapter officially through SPWLA.org. Question and answer to be kept at the end of lecture, and kindly keep your camera closed and only for lecture for sure. And any question and answer will be kept at the end of lecture. Thank you all, and the floor is yours, Mr. Andy.
Okay, thank you very much.
If you like to, if you like to introduce yourself in more details.
Yeah,
okay.
I will do. Yeah.
Thank you.
Okay. Can you see the presentation?
Yes.
Okay, that's great. Okay. So, yeah, hello everyone, and thank you for inviting me here today to present. Oh, just noticed the Teams is on the wrong window. There we go. So yeah, thank you for inviting me here to present today. For those that don't know me, I'm Andy McDonald, the product champion for machine learning and Python within interactive petrophysics. And I've been in the industry for about 19 plus years, covering a variety of geoscience and petrophysics roles. And that includes working with Baker Hughes as a geoscientist working on logging well drilling and borehole acoustics. And since then, I've been working with Synergy and Geoactive. So we've changed name throughout the years. Originally Synergy, now yeah, went through to LR and then Geoactive. So you may have heard one of our names in the past. In recent years, my focus has switched to understanding AI and Python tools and how they can be integrated into petrophysics. And not only have I been focused on the algorithms themselves, I know there's a lot of great algorithms out there for AI, machine learning, but it's all too easy to be attracted by all the nice flashy algorithms. But where my main interests lie is in the data quality issues, and I'm sure everyone here is aware of the data quality issues we face when working with well logging data. And that's where my focus has been, how we can improve that, how we can go through the process of machine learning in a transparent as possible way, and also ensuring that we've got good quality data going into them. And as part of that, I've been working on our latest module, or the latest updates to our module, called Experienced Eye within IP. And this module is used for automating the feature selection and machine learning prediction workflow, and providing a transparent comparison between different models. Even though the module's been around for a couple of years, we've made some exciting changes to it in the latest update last month, and that's what I'm going to be covering towards the end of the presentation. So what are we going to cover today? First, we're going to have a brief introduction to IP. I know not everyone uses IP, so we'll just give a very brief introduction to it. And then we'll look at a specific part of the machine learning workflow, which is feature selection. And before we move on to looking at the Experienced Eye module and the actual workflow. And then, yeah, I'll be happy to answer any questions that come up at the end. So as an introduction, so IP, or interactive petrophysics, as it's also known as, it's been around for quite a long time, since the late 90s, early 2000s. And for those that are not aware of IP, it's one of the industry-leading subsurface data interpretation software packages, and there's a strong focus on petrophysical workflows that cover a wide range of applications, from reservoir characterization, so doing our clay volume, saturation calculations, cutoff and summation, etc. And we also expand into geomechanics, borehole image interpretation, cased hole logging, and a variety of other applications. So with that, we have a wide user base, and even though it's petrophysics at the core, we can support geologists, geoscientists, well integrity people, production engineers, geomechanics, well operations, and geophysics, and we can support all of those disciplines all the way through the entire asset life cycle, all the way from exploration, all the way to or through appraisal, development, production, abandonment, and then yeah, pretty much the whole life cycle. We've got a fair number of modules in IP to do that. And we also have modules, when we're going to see one of them today, which focuses on machine learning, and that is quite a growing topic these days, isn't it, with machine learning, AI, and all of the latest tools. So the tools that we have in IP cover things like curve prediction, so repairing missing logs, and computing continuous curves from discrete data. So if we've got discrete core measurements, say permeability, we can take that data, train a model, and make a continuous curve prediction. And we also have tools for predicting facies or reservoir rock types using clustering, self-organizing maps, and we can then leverage those to do our permeability calculations for different facies if we need to. So I'll get into the main point of the presentation, which is about feature selection. So feature selection is a specific part of the machine learning workflow. And as I said, machine learning is increasing in popularity within the geoscience domain, but it has been around since the 1960s, I believe, where we started working with Markov chains to do some sort of prediction, and then progressed into, I believe, clustering and algorithms along those lines, and into the late 60s, 70s. And then as we progress through time, machine learning started to become more important, certainly from, say, the early 2000s. It was just starting off to be a little bit more popular. And then in the last decade or two, the popularity has suddenly increased. And then in the last, 5 years, 6 years, the generative AI or foundation models in AI have started to become much more prominent. I'm sure we're all aware of ChatGPT and Gemini and all the other powerful tools out there. But machine learning, as anyone that's, I guess, attended the previous webinars will know a little bit about machine learning. And it's basically a subset of AI. And what we're trying to do with machine learning within petrophysics, I guess, is to automate and improve our petrophysical interpretations with those tools. So feature selection is about identifying the most relevant features or variables from a dataset. Now, you'll hear the term features, variables, input curves, and different other terms. And basically, we just mean well logging curves. That's what we are calling them. And the terms can be used interchangeably. In the machine learning world, it is features mostly, or variables. But obviously, we work with well logging curves or well logging data. And what we're trying to do is build the most efficient model possible and get the most accurate as possible as well from that process. And by focusing on the feature selection part of the process, we can help reduce training times. So if we had 20 features or 20 input curves, not all of those are going to be relevant to predicting porosity, for example. So if we take out the least relevant curves from that input data set, then we can reduce the training times. And that's more important when we come to big models, say more advanced neural networks, or I guess even into generative AI these days. And with fewer features, we can make the models easier to understand. So by having fewer features, we know what inputs are going into the model. So we have a rough idea of how that model is being driven by those inputs. And there are other tools to understand how features are influencing the results as well, but that's a separate topic. But this part occurs sort of before applying machine learning. And we can also reduce overfitting. If we start feeding lots of data into the algorithm, there's a high chance that the models could overfit, which basically means memorizing the training data. And then when we present new wells to that data, the models won't be able to generalize very well to that. So we want to reduce overfitting as much as possible. And more data does not necessarily mean a better model. So we can just keep it to the most relevant and most influential input curves to help improve prediction accuracy. So where does feature selection fit within the machine learning workflow? So I'll just give a quick overview of this workflow that we've got here. So when we do a machine learning project, we need to understand what we're trying to achieve. Are we trying to predict fascies? Are we trying to predict permeability or missing curves or repair data? So we need to have an idea at the start about how we want to process that data and then what model we want to select. We then gather up all the relevant data sources, so all of our LAS files, well data files, etc. And then we take that data and split it into testing data set, which is then set off to the side. This is also known as blind testing. And then we take our modeling data and go through the process of exploring it and then exploring it, QCing it, and carrying out data repair. And then we go through the process of feature selection. So this is where we select the most relevant features for our data. We then go through the process of training and validating our model. So we try to tune the parameters or the hyperparameters of our model. And that is when we're using that validation data set. And we then go through the process of evaluating it. And then once we've completed that process, which is iterative, we then apply it to our blind test data. And that tells us how well our model is performing on completely unseen data. So the validation data set used within the training process is partially seen by the training, by the model, as you are looking at that result and then tweaking the parameters and then trying it again. So it's partly seen there. Whereas the blind test data is set aside and then we can verify that. So with feature selection, in this example that we like to use is where we have a target curve. In this case, it's porosity. So using our domain knowledge, we could pick the most relevant input curves, say gamma. We can get an indication of clay content, which can then impact the porosity. We then have density, which or bulk density, which can then be used to calculate a porosity, neutron porosity as well. And same with some of the other curves within this list. However, there may be cases where there's hidden underlying structures within the data that we might not immediately associate. We may have bias towards certain curves within our interpretation, so we stick to those curves in general and maybe forget about the rest. But that can be a process of trial and error if we want to swap curves in and out and then see how they perform on our machine learning models. But there are numerous automated feature selection methods, everything from a simple Pearson's correlation, where we're looking at the correlation between two curves and seeing if they're highly correlated, anti-correlated, or there's no correlation between them. Then we have backward feature elimination, and that basically we start with a data set of all of our available curves, run an algorithm such as a multilinear regression, and then we go through the process of feeding those curves into it, evaluating the results, such as using the p-value, and then we drop the least significant curves from that process. And then we repeat it again. Then we've got experienced eye feature selection, which I'll come on to. Is basically one of our unique feature selection models that is tied to domain transfer analysis, and that is using the actual machine learning model to do that, and that is more of an embedded type of feature selection. So just to give you an illustrated example of feature selection, so here we have 14 input curves on the left, or 14 features as you like. So we've got rho B, PEF, delta rho, DT, all of the common curves, including some gas curves, and then we feed them into a machine learning model. And as part of this study, what we used was a simple Pearson's correlation, which is a filter method, and that is used for, as I said, measuring the strength of the relationship between two variables. So values can range between -1 and +1, and values that are closer to 1 or -1 indicate that there's a strong relationship. Either it's a positive relationship or it's negative, it's an anti-correlation. And then those values that are closer to 0, there's no relationship. So as part of this study, what we did was we converted those values to absolute values and then applied a cutoff in 0.1 increments all the way up to 1. And we run the model multiple times and then gradually increase this threshold. So to start with, we had all 14 curves in and we fed these into our machine learning model. And as you can see, the result on the right, where we've got our actual versus predicted porosity, we can see that we've got quite a wide spread of results for our prediction. And we can see that the metrics are relatively poor as well. And I'll come on to metrics in a little bit as well. So we then proceeded to iterate through the process, and then we start losing some of the curves that are least relevant. In this case, we dropped out delta rho and C1, C4 gas curve. And we get a slight degradation in our model by dropping those and relying on the remaining 12. But as we start to progress through it, then we start to see improvement within the model. And this is iteration 5, so we probably at 0.5 of our Pearson's correlation value. And we're left with 7 features in this case, and there's a slight improvement. And then eventually we get to iteration 7, and we're left with 3 features. We did carry on down to up to 0.9, but there was very little improvement beyond that in that case. So we're left with 7 features, which are bulk density, acoustic compressional, and I think it's a total gas, if my memory is right. And you may think rho B dt absolutely fine for our porosity prediction, but the average gas there was thought to be an indication that there could be a light hydrocarbon effect affecting the results. So that's probably why the model included that, or why it was highly correlated with porosity. So that was kept in. So that goes through the process of removing the features, and we can see that we end up with a better model in terms of fit with our one-to-one line. But we can see in the lower porosity intervals that our predicted porosity is reasonably good. Okay, there's a little bit of scatter, but in the high porosity intervals, there is quite a large spread in our prediction. So that might indicate that we might need to find other curves to bring into our model, or if we got to separate out the formations or the intervals and then do a separate model to see what's happening in that upper interval. So following on from that paper, so back in 2020, 2021, my colleagues and I were working on a new feature selection method, which is experienced eye feature selection. So we've got experienced eye, the module, and then there's a feature selection method within that. And that is based on domain transfer analysis, which is a unique module to IP that utilizes a specific set of mathematics and equations to derive a model from the input data. So unlike statistical methods and unlike, say, a neural network, when we run with the same data in DTA, or domain transfer analysis, we end up with the same result. But if we change the data or change the interval, then that changes the data points going in, and then we get a different result. But if we kept everything constant, then we can keep running the model and we should get the same result. Whereas, say, with a neural network, unless you're using a fixed seed, then you may end up with different results each time because of the way the neural network reinitializes the weights and the biases, etc., that are behind the scenes. And as part of this process, we get impact factors or influence factors for each of the individuals' input curves. And I can't remember what we were predicting in this particular one, but we can see that the curves, porosity and gamma ray, V clay and DT are all very high and tie in relatively well with the target curve in this case. And that's just giving you an illustrated example of what the influence factors are. But if we look at a more concrete example where we are trying to predict a continuous permeability from core data, we carried out a few case studies as part of that paper, and in this particular case study, we were looking at the Tarossa field from Western Australia, where we just took 2 wells, one for training, one for validation, keeping it simple just to test the process. In this case, the target curve was permeability, and from the dataset, we had 9 input curves that you can see here, standard curves that we might expect. And we also passed in our TVD as well. And as part of that process, what we did was we ranked the inputs based on domain expertise. So myself and a couple of colleagues looked at the input curves and thought, well, what ones would we expect to correlate well with, say, core permeability? And then we just went with that for the domain expertise. And then we tried to compare the different feature selection algorithms. And what we found was for predicting permeability, the inputs were then ranked in relation to that. And we have rho B, gamma ray, N-phi, and PEF that we thought would be useful for predicting a permeability curve. And that, yeah, so when we run the other automated feature selection methods, so Experienced Eye, we then found with that method, we had rho B, gamma ray, and neutron porosity, tying in very well with our domain experts' opinion. And then the other methods, some of them had slightly different orders, but that's fine. And then some methods, such as a lasso regression, and then looking at the coefficients, there wasn't very much correlation there. So on the right, we can then see a spread of the results. We don't have the actual core permeability points on this particular plot, but the point of this plot was to look at the variability in the different results. So when we used combination of ETA and the different rankings, we got a fairly consistent grouping of the output curves. Whereas if we used a more traditional, say, neural network, then there was quite a wide spread of results. And same with MLR, it's a little bit tighter, but there's still a spread of results. So this was just sort of validating the Experienced Eye feature selection method itself. And as a result of that, what we found was there were a couple of issues with the whole process and not with the actual results. And the process to do this was an entirely manual process, and it can be time consuming. So to give an example, so if we started a single run through this very simplified workflow where we take our data, select features, apply a machine learning model, and then evaluate the performance, that's fine. It's a single pass through the algorithms. But if we look at the results from that, there could be a lot of uncertainty around the correct inputs and what other algorithms would give us as a result. So we needed a way to compare them very easily and very quickly. But if we expand what we've got here and we start comparing 3 different feature selection methods that we've previously mentioned, and then 3 different machine learning models, we end up with 9 separate runs through this process. And that's not accounting for trying different combinations of inputs. So that can start to build up as you go through the process, run the algorithm, view the plots, and try to understand if the results are different. And then if we start taking groups of, say, the top 3 to top 8 ranked features from each of these methods, each of the feature selection methods, we then end up with 54 separate runs through this process. And as you can imagine, doing this manually is very time consuming, several hours to days, depending on how much time you have available to work on this. And you would still have to compare the results through the regression metrics in various plots. So that can start to eat up the time to do this. And the other issue that we found is we can't just rely on a single metric. So we can't just rely on R² alone when we're trying to compare the actual to the predicted. So we start to look at a number of different metrics as well. And some of these you may have come across: mean absolute error. We're looking at the average differences in the actual versus predicted. Mean square error, we're averaging the square of the error difference between the actual and predicted, and then that can amplify the effect of outliers. And then we take the square root of that to bring it back to the original units of the curve. So when we're using mean square error, it becomes an inflated number, and doesn't really tie in with the original target curve, the curve units of that target curve. And then we have the traditional coefficient of determination, R², which we're all familiar with when doing a linear regression. And this measures the variance in the prediction results that can be explained by the model. And what you can think of is the mean absolute error can tell us the average size of the mistakes. Root mean square error tells us whether any of the mistakes are big enough to cause concern, so if we've got any outliers. And then R² can tell us how much variation in the predicted value that you are capturing. That's all great. We can look at the metrics. But if, for example, we have an outlier in our predicted porosity, we can see that the metrics start to vary slightly. But if we just rely solely on R², so we're going from 0.95 to 0.92, then we could be misled into thinking it's still a great model, it's above 0.9, we can carry on with that. But if we start looking at the other metrics, such as mean square error, we can then start to see that it's significantly higher than the previous model, suggesting that something is pulling at the result. And we can also see that the outlier impacts the mean absolute error, not greatly. So in this case, 3.5, and the previous one was 2.3. So there's very little variation there, but we can see that the RMSE, root mean square error, goes from about 2.45 to 4.6. So that's quite a change there. And obviously, if we've got more outliers, or if we've got offset predictions, so we're predicting higher than actual, then we can see that in the results. Now, whilst these metrics can be useful to help quantify the error between the actual and the predicted, it can't really tell us where the issues are. And this is where we need to go beyond simple metrics and start leveraging data visualization tools, which is, again, one of the reasons why we developed and expanded Experienced Eye's module, the IP's Experienced Eye module. So back in 2023, we developed a new module from the ground up and started to put the vision of bringing those issues into a single module, and that would allow us to visualize the common metrics and the charts in a single place rather than trying to pop open separate cross plots, log plots, etc. So not only does this streamline and automate the process so we can pass data in, we can then run all these models in tandem, and then we get the result out and we can compare it all in a single place, which is one of the key benefits to this module. And also the interactivity allows us to explore the charts and explore the metrics and explore the training and the testing data set and see whether we are underperforming or generalizing or just overfitting. So we can then see on the crossplot, as we saw earlier, we can then start to see how much of that error can be identified within the actual crossplot. Where is it? Is it in the high porosity intervals? Is it in the lower porosity intervals? And then we can also see the comparison of different feature selection methods on the prediction models. So where does Experienced Eye sit in terms of the overall machine learning workflow? So that area shaded in green here indicates where the module is pretty much covering. We carry out the feature selection, do the training validation or training test data split, and then we iterate through that process and evaluate the model. And then once we're done, we can then export that model and then use it to make predictions on new wells or new data that we have available. So the idea behind the Experience Eye module is that we take the input curves and carry out some data quality checks. We look for complete rows of data. So if we've got 4 input curves, then all 4 input curves must have values at a specific depth level for that depth level to be carried on to the modeling. And if one of those curves has a missing value, then that row has to be dropped from the process. Now, not all machine learning algorithms require that, as some can handle missing values, but the ones that we've focused on for this uses existing IP machine learning algorithms. So once we've done the data quality checks, we then carry out the feature selection model process and can start to group the top 3 to the top 8 ranked features from each of those feature selection methods, and then pass them into a machine learning model. And that's where we then evaluate the performance and get our metrics that we've seen before. So with that, at the start of this year, we started to work on enhancing the module. So previously it was single well, and it focused on a single well, and then we're trying to view the metrics, and there was some interactivity there. But one of the biggest changes that we made was to make the module multi-well aware. So previously, as I say, it was single well. We now can train on multiple wells and test on multiple wells. And that allows us to bring in much larger quantities of data from across the field or a project and see how they impact the result, and also see whether we've got any problematic wells that we can either drop from the model or sort of revisit and see what the issues are. We've also added a lot more visualizations that can help us understand where the error is and how it compares to other wells. So we can see how stable the models are with varying numbers of inputs. We can see how the current, say, an active well compares to other wells. And we also have the interactive log plots as well, so we can start to see where that error is. So not only do we get the metrics to quantify how much of an error there is, we also see where that error is within the actual well. And with the cross plot, we can also see. Oh. Sorry, someone was talking there. So yeah, with the cross plot, we can see then where that error is in terms of the actual result. So whether we're in, say, low porosity intervals, we're under predicting or over predicting, or high porosity intervals. So it gives us a complete overview of, I guess, how well our models are performing. So what I'll do is I'll jump over to IP, and we can quickly run through the module and see the different parts of it in action. So with Experienced Eye, I've got, I think I've got 12 wells within this particular model that I've run earlier. And what we're trying to do is predict our shear slowness, our ACS curve here. And then we've passed in a multitude of curves, so standard logging curves, caliper, density, gamma ray, neutron, resistivity curves, and a couple of gas curves as well. So we've got one gas ratio and the gas X curve in here. But with this grid, what we can do is add in the wells, and curves are populated automatically. So I'm going to select a well at random. I don't know if it's got all of the curves, but if I select one at random, we then see that when we populate this, we get red highlighted boxes that can tell us this curve is missing. We can't use this well. And if I try to run it, it will then give an error saying that it can't run that with that well. And then obviously it's missing the target curve, so it can't build a model from that particular well. So that's one of the nice things here, is that we can start to see where, if we start adding wells, do we have all of the available data. So remove that one off of the list. And then with the rest of the module, so if you are familiar with any of the machine learning models in IP, then you will be familiar with this grid where we have the curves, and then we can easily populate the grid per well, and then we select the intervals and any additional properties as well for visualizing that data in the results. We can also select data based on either a random point selection, so we randomly select points for the data, which is a common technique, or we can select certain wells or certain key wells as training wells, and then additional wells as testing wells for checking our results and tuning the model. So we can split the data that way, or we can use an automatic random point selection. So with that, we can then go into the options, and this is where we can then start to specify certain options. So one of the issues with some machine learning models is the influence of multicollinearity, where we're passing in curves that are exactly the same or very highly correlated. And that can double down on those input curves in the machine learning model, and as a result, it can influence the final result. So as a quick way, we have a Pearson's correlation cutoff. So we're looking for a highly positive correlation between the actual curve and between one of the input curves and the target curve. And if that is close to 1, then we drop it. And a good example of that is if you have two porosity curves that you've been delivered and you find one is in decimal and one is in percentage, those curves are going to be exactly the same, just off by a magnitude in terms of percentage and decimal. So what do? Well, we can use Pearson's correlation to see, are they truly correlated with each other? If they are, drop one of them, and then we can carry on. We can then select the training percentage. So we use 70% for training our model, and then 30% is used for tests. So that is a user variable that you can change. So if you've got a massive data set, then you could bump that number up to 80, 90% and reduce the amount used for testing. But if you're working with a small data set, then you may want a larger testing percentage. So you would then reduce that number down to account for that. And then we've got the choice of feature selection methods. So we've got Experience Eye feature selection itself, which is, as I say, is related to DTA. And then we've got Pearson's correlation and backward feature elimination. And one of the things that we decided to keep in is a user-defined order. So we're not excluding the petrophysicist or the interpreter from the process. So if you still want to put in curves and see how they compare to automated methods, then you can happily do that and then see if what you know can beat the machine, as it were. So there is that option. So you're not restricted to using these algorithms. You can use your own order and still run them through the other machine learning algorithms. So DTA, multilinear regression, and neural network. So once the model's run, I won't run it in this particular example as it can take a few minutes. So don't want to disrupt the webinar. So I'll go on to the next tab, which is looking at the data summary, and this just provides a transparent look at it provides a transparent look at what the model setup was, what curves were used, what actual percentage went through, because sometimes when selecting points for each of the wells, then we might be slightly off from our 70-30. So in case we're 70.2, 29.8% in that example in terms of our data points. So it gives you full transparency of what was used, what was dropped, what the settings were, etc. So that's great for copying out into a report and keeping things clear. But the real power is when we come to the results tab. And with this results tab, what we have is our different ranking methods here. So we've got Experienced Eye feature selection, which has our influence or impact factor. And we have AC coming out on top, which is compressional. And that is, I guess, what we would expect to happen with our shear curve. Compressional is going to be highly correlated with the shear. So that should come out on top, and we're happy with that. And then similar with density. And then we've got additional ones that are being picked up that may have some underlying relationship with the shear that we might not see. But to do that, you would have to look at multiple cross plots of these input curves versus the target and see what the actual relationship is and if there's any correlation there. So this just almost skips that step and gives you it in terms of yeah, a few numeric values. And we've also got our user-defined order, which will then be used in the machine learning models as well. So the next part down is where we're looking at the model performance grid. And I'll just pop that back to R squared just a second. We can then see the R squared values for each of these results. So this is an aggregated grid. So we've got 12 wells in here, and then we've got 12 wells of metrics, or 12 separate metrics per cell here, and then it's aggregated and averaged across all of those 12 wells. But these can easily be turned on and off, so we can then start to see the influence of certain wells. So we can then boil it down to a single well or remove some of the wells that we don't need. But with this grid, it's all fairly green at this point, so we can just change the values here on the shading just to change the color a little bit, and then we start to see where we've got good models and then where we've got slightly poorer performing models. Now, the thing is, we might think, right, I'm going to go to the best model, which is neural network with backward feature elimination. And that has the highest R squared in this particular modeling scenario. But what you'll see down the bottom is the individual well log plots for each of the wells that we've used, and we've got the actual measurement versus the predicted measurement. So these can easily just be popped out into a new window, and then you can get a better understanding of how that prediction is done in each of these wells. And then these are fully interactive in terms of moving up and down and zooming in and out. But you can see that in some wells we're slightly off. We've got a slight under prediction here in this particular well, certainly in this upper interval. Same on the next well along, and a slightly less under prediction on the last well. So that's not brilliant, but if we ignored the fact that that's got the highest R squared, and then we look at the RMSE, we can see that that is one of the highest or one of the higher values for RMSE, which suggests that there is some issues with that model in terms of that we see this offset. So relying on R squared alone, we wouldn't see that. Whereas if we use the other metrics, so mean absolute error and root mean square error, we can then see that issue. But instead, if we go to, say, DTAEEFS, which is a bit of a mouthful, we can see that even though that R squared is lower, so 0.86 versus 0.9, we can then start to look at the plots and see that we've got slight offsets, say, near the top, and these outliers here could be adjusting that R squared score and then bringing it down. But if you look overall, where the wells that were over here with 2S and 6S, then excuse me, with 2S and 6S, we can then see that there is a big improvement in our prediction versus the actual measurement. So that is why it's best to rely on other things other than simple metrics alone. But we're not only limited to looking at log plots within this module, we can look at a multi-well cross plot, and we can see all of the wells plotted on top of each other and how they relate. And then if we select the color by well or tick the color by well option off, we can then cycle through the different wells and see how they compare relative to the rest of the wells for the current selected combination here. So if I move over to, say, the neural network, then we can see that we're severely under predicting in the slower intervals up here, whereas down here we're reasonably okay. A little bit of clutter, scatter there, and whereas DTAEEFS here, is fairly consistent around that 1-to-1 line, and there are a few outliers up here as well. So the idea is that we can then see where the error is in terms of the predicted value versus the actual. And from that, we can then start to dive into the single well analysis plots. And this allows us to look at the same multi-well crossplot in the top left here, but we can also start to look at the histogram, so looking at the distributions of the actual versus the predicted. And then we've got the individual log plot along the bottom that we can then zoom in and move around to see where we have issues. So in this interval here, where we're quite slow, we've suddenly got points that are being predicted out at what, about 400, 450 microseconds per foot up here. And same with this interval here. So we can get an understanding of where the error is occurring and where it is also actually good. Whereas if I go back to this poor one where we've got a slight offset, we can see that the histogram moves off, and we can also check whether it is in specific wells. So we can cycle through the wells, and then we can see that some wells, like this one, where we got things getting faster as we go deeper in this particular one, we can then see that there's quite a large separation at the top, and then that correlates with our crossplot up the top and our histogram as well. We can then start to quantify how much of an error there is versus, say, maybe a better performing model where we're generally in agreement with the histograms, generally in agreement with the logs. Again, there's a little bit of offset, but it helps with understanding that process and the results. So once we start doing this in multiple wells, we can view the box plots or box and whisker plots. And this, as I say, for each of these cells, there's, so in this case, 12 wells worth of metrics behind each cell here. And then we can start to see them displayed on the box plots here. And these box plots include all of the values from the top 3 all the way down to top 8. So there's quite a lot of points on there, and then this allows us to understand what wells are performing really well and what wells have quite a range in values, and this is probably related to what one was it, 32, did I say 2S 2S in pink here. Then that's the well here where we've got quite a large variation in results. So that well, there's something going on there. We might want to check it, data QC it, and verify that that well is good. Have we got any issues in that well? So this allows us a deeper understanding of what wells are having issues and what ones are doing relatively well. And I should say that we can view the training subset of the data, so we can predict onto the training data as well as predicting onto the testing data. So you can then start to see whether you're overfitting, where your test results will be lower than your training results, and you can understand whether you're going to generalize well to new data. And also with comparing different models. So in this case, we're comparing machine learning models, so DTA, MLR, and neural network. And what we're looking for is, I guess, consistency between the results. So there's a bit of separation here at 5 input curves where the model starts to underperform for backward feature elimination and EEFS in this particular case. And it also gives us an understanding of how stable the model is in terms of adding more input curves. So if we've got a fairly consistent grouping here, like we do here, then we can see that the model is fairly stable if we add more input curves. It's not going to degrade drastically. Whereas maybe some models, we might see it decline as we add more input curves, or we may see it improve as we add more input curves. So by understanding how each of the machine learning models compares with the feature selection methods and how, say, the different feature selections, so how we're looking at the feature selection methods here, we can then see how that's comparing across the board. So we can see PC, Pearson's correlation, backward feature elimination, and then our user defined order as well, and EEFS. So we can then start to see how those different feature selection methods impact the machine learning models. So the other part, as I say, if you look at the training versus test, so this allows you another view of it, and we can see here that 7 input curves for this particular model. We can then see that the training data has a lower R-squared compared to the testing data, which gives us a cause for concern. So we might want to review that model or skip it entirely. But if this was flipped and we had the training data on top and then the testing data below, then we could say that the model is memorizing the patterns and it's not generalizing very well. So it's performing worse on the test data compared to the actual training data. So having all of these insights helps us identify what the best models are and whether we want to take any forward, and also gives us justification for dropping certain combinations or certain models. So if you're providing a technical report, then you can put your justification down as to why you've selected certain models, and this sort of backs it up for you. So once you've selected your model, I'll just pick this one at random, we can then right click on it, and then that launches into that particular module. So in this case, this is DTA, or domain transfer analysis, and it populates it with all of the input curves that you've selected. So we've got 4 input curves here, which yeah, so we've got our input curves, 5 input curves here, sorry, and then we are using those to predict ACS, and everything's all set up for you, and then you can come in and then start adding an additional well, and if the curves are present, then it will populate with that those input curves ready for you to use, and then you would untick that well for training so that you are using only the wells that you've built your model with, and then applying it to new wells. So this would also apply if you have wells where you are, for example, using core data to predict permeability. You may only have a very limited number of wells, so you would use them to train your model, and then any additional wells where you don't have core data, then you would bring it in here and unselect it for using the well for training. I think that's pretty much it for looking at the module. There's a few other tweaks and parameters that you can adjust in here, and then, as I say, visualize the impact of the results. So if you wanted to view a single well, for instance, 318-1, then we can look at that one well, and that's the metrics that we are viewing for this particular well. And as you can see, each of these X's on here represents a single value on this grid. Okay, and if I go back to PowerPoint. So in summary, the Experience AI module is a great tool for streamlining and automating the process of selecting curves and features for your machine learning model process, and also does it in a sort of a transparent way so you can see the impact of the different input curves on the different machine learning model results. And we've made it multi-well aware, so you can bring in wells from across your project or your database, and then use them for training the model, and then using that to make predictions with. And it also gives you the flexibility to specify wells for training, testing, or using random point selection, which is a very common technique. And the powerful interactive visuals make it easier to explore the results. So you're not only looking at just a single metric, you're looking beyond that metric at different charts to be able to understand where the error is, how much of the error there is, and whether it is at, say, upper end or lower end of your target variable. And you can start to quantify that visually. And we've also made speed improvements. So as you can imagine, for passing in tens of thousands of data rows into these models can start to bog things down. But we've made it in a way that we're making use of multiple threads on your machine or computer, and that helps speed things up, certainly with the prediction algorithms. And I think that is me. So I'm happy to answer any questions if anyone has any.
So first of all, I'd like to thank you for this formative and fruitful lecture, Mr. Andy. I believe what you present reflect that interactive petrophysical software is really adaptive. This new trend in AI machine learning in very user-friendly way in the IP, you know. So I believe there is a couple of a question in the chat box, if you can see them.
2 seconds. Where's the chat gone? Okay, got it. There we go. Right. Okay. Okay. So quite a few questions here. So the first question, plugins from Geoactive which link IP with Petrel, and in specific help us load PLT logs into Petrel instead of loading them manually. So yes, we do have a Petrel connector within IP, and actually my colleague Ross Brackenridge is here, who's very familiar with PLT. I don't know if you have any comments on that. Don't want to put you on the spot. Okay. But yes, IP does have a connector for that. And it's the question, how did you get the actual ACS shear? So the ACS for that data set that I was showing is actually a measured shear. So that was part of the original logging data that was there. So it's not actually a predicted one. And then as we went through the process, that's where we're trying to recreate that curve, as it were, within the different wells. So hopefully that answers your question there. So next question, Sanjeev. How can Fershey's curves be incorporated and appropriate weightages assigned in order to effectively discriminate between homogeneous and heterogeneous reservoirs? So at the moment, we aren't really accounting for that. We don't bring in a discriminator curve for doing the different fascies, but that is something that we are looking to expand on, I guess, well, hopefully next year, to be able to account for that. And I think that's it.
Yes.
Yeah, I think that one
I
answers
believe,
that.
yes,
Yeah.
I believe the subject is a little bit advanced. Okay.
Yeah.
Yes. So actually, I have like one or two questions. So for this technology, if somebody want to like proficient more in IP, is Geoactive provide some kind of like training for this one,
Yes,
for this
I mean
webinar?
that's possible through dedicated training sessions or demo sessions, and we can do that sort of thing to go through the whole process. But as you saw, it's fairly simple to run through. But yeah, we're always open to doing that sort of thing to help the users.
Okay, that will be great to know. And my other question is, I saw you integrate several like wells, like a multi-well. Is this technology can be done the same if this set of well was like for production logging, for pulse neutron, I don't know, like not open hole logs. It can have the same, or right now it is dedicated for open hole logs.
What with the visualizations? You mean?
I mean, if you have like, for example, you have several PLTs, okay, in same area, and like some of them is missing a few passes, and you want to find this missing pass, imputed part, okay, something like that. I mean, this technology right now is for open hole, or it
Yes.
can't be used for case for case.
Well, it can be used to predict anything in terms of if it's a continuous curve, it can be used to predict that. But the idea is then once you've identified a suitable model, you would then use it to, I guess, fill in any gaps that you may have in other logs or other data sets.
Okay. Yeah, reason of my question is like right now, like in the last, I can say 5 to 10 years, like case holes start to be a little bit aparted from open hole, and many people either go in case hole direction with PLT, multi-array tool, okay, pulse neutron, or go with the direction of Petrophysics. Even the companies in-house start to make like 2 separate team for this one.
Yeah.
Okay.
No, I think that's been like that for, well, certainly from the service side of things, with service companies. I know at Baker Hughes, what, 15
they
years
start to
ago,
put
we
like a
were
domain.
cased hole and open hole
Yes.
back then as well.
Yeah, I mean, even in operator house, like mostly in operator, like there was one guy called Petrophysicist, and right now they changed it, like they called it data processing or hydrodynamic petrophysics, which is responsible on PLTs, voltages, and the other guy, Petrophysicist, is for open hole on all these studies. And they start to separate the teams, you know.
Okay.
This is the thing. Okay. So I have no more question, and
one's just come in there.
Yeah, Mr. Sanjeev.
Yeah. So can you get the zonations or a particular interval into your model? So at the moment, the module is using an interval. So you specify a top and bottom interval, and then it just uses that. We do have enhancements or enhancement cases for bringing in zonations like our curve prediction modules. So like DTA, where you can bring in your own zonation, so you can select intervals or you can select based on formations. But that's something that again that's in the planning.
Okay. So I believe now we can conclude the webinar. Any last word, Dr. Mohammed?
Yes, Mr. Mazen, I would like to thank Mr. Andy McDonald's on behalf of SPWLA Iraq for your insightful and highly informative presentation for today. The attendees, thank you for your participation in today's webinar. We deeply appreciate your continued interest and engagement. On behalf of SPWLA Iraq, we would like also to extend our sincere thanks to all our sponsors for their continued support. We wish you all the best and look forward to welcoming you to our future events. Goodbye.
Goodbye. Thank you, Dr.
Thank
Mohammed.
you.
Yeah, so I would like Mr. Andy for his time, Geoactive company, Dr. Mohammed Jawazi Al-Abidin, and our sorry, our attendees. If this will be our last webinar for this year, so Happy New Year, or maybe we see you next month. Okay, it depends. So have a great day all. Thank you.
Okay. Thank you, everyone.
Thank you.
Thank you,
Bye
Mr.
bye.
Mazen. Thank you, Mr. Andy. Bye bye.
Thank you.